In this movie, we're going to discuss this question: what conditions must be met before we can conduct a hypothesis test with a mean? Now, as we established earlier, all inference procedures are based on probability. So when we ask this question, what we're really asking is, when can a normal probability model be used to predict the behavior of sample means? Now, obviously, we have to have a random sample, since probability is based on seeing patterns when repeating random events. Now, with sample means, we know from our work on sampling distributions that if a variable varies normally in the population, then random samples will have normally distributed sample means, and this occurs regardless of sample size. Let's look at a familiar example from our work on sampling distributions to remind us of this fact. Birth weights are normally distributed in the population of newborns. When we collect thousands of random samples from this population and graph the sample means, we see a normal distribution, even for very small samples like 9 babies at a time. So we can use a normal probability model to determine how likely or unlikely given sample results are. This is an illustration of the first row in the conditions table. Now let's think about situations where the variable is not normally distributed in the population, such as commute times for a small town in Florida. Now, sample means are not normally distributed for small samples. In fact, the sampling distribution looks pretty much like the population, which is really not that surprising when we're only collecting 2 people at a time. But if we increase the sample size, the sample means become more normal. Our general rule of thumb is that if the sample size is greater than 30, then sample means will be close enough to normal to use a normal model. What this is really saying is that the area under the normal curve will give a fairly accurate estimate for the probability of sample means occurring in specified ranges. This is an example of the second row in the table. Now we're going to investigate the gray area. In practice, you will see statisticians use a z-test when the sample size is smaller than 30, even when they don't know that the variable varies normally in the population. Okay, so when this is done, it's because they look at a single sample and they make a judgment about whether or not the sample looks fairly normal. At least they look to see that the sample is not heavily skewed and it doesn't have outliers. Then they make the argument that based on what they see in a single random sample, that they can be reasonably sure that the variable has a normal distribution in the population. Now, there are of course more advanced techniques for describing just how close a sample is to normal, but these techniques are beyond the scope of this course, so for now, we're just going to eyeball it. Now, what I've constructed here is I have 3 different populations, and they're hidden from view. I'm going to take samples of size 15 from each of these populations, and I will do this several times. I want you to see if you can identify the normal distribution in the population just by looking at the shapes of the samples. Okay, here's our first samples. Each one has 15 in it. Look at the shapes. Which population do you think might be normally distributed? Here's a second sample, and a third, and a fourth. Did you predict correctly? The top and the bottom populations are normally distributed, and the one in the middle is heavily skewed to the left. Now, I'm going to collect just a few more samples so that you can again compare the shapes of the samples to the shape of the population. Now, obviously, eyeballing is not a very precise method, so if you proceed with the test and your sample size is less than 30, it's a good idea to include a disclaimer with the conclusion to your hypothesis test. You might want to say something like this: based on the sample, I'm assuming the variable is distributed without strong skew or extreme outliers, in other words, fairly normally, in the population. The conclusion drawn from this test is valid only if this assumption is actually true.